Okay, let's start our optional Lab 2 video. Let me, yeah, so we have a little bit different topic this time. We're going to think about minimization. So as you have followed through your reading, you will have seen the minimization problem that's in the second part of the Anderson chapter. And then in this lab, we're going to do our first minimization problem. It's going to be a simple two-option diet problem. And of course, there are a couple of optional readings related to diet type models because we are going to think about that nutrition and optimality of diets as our semester sort of project or our theme that lets you continue to work and revise and build a little bit bigger model that you have a little more ability to design, right? So week to week, you get these small sort of building block pieces, and we demonstrate some different things that we want to learn, but we don't have a situation in a lot of those where you can sort of put two of the building blocks together and sort of see how it works when you do multiple things, and especially where you get to design the questions. So that's why we have the sort of theme project, and we do the diet because one, it's probably not something any of you are specifically doing, and so it's this sort of fresh and different idea. Two, lots of people have experience with food and food purchases, so you have some decision making background that is common to everyone about budgeting and trying to meet certain requirements. And three, there are all kinds of cool policy and marketing questions around the way we interact with food and the way the government tries to think about regulating what people can label as food. There's a lot of marketing done around what kind of diets are good and you know, giving people programs for eating. We have government policy that actually designs a specific program of diet and uses that to index the costs for anyone, military or anyone on assistance or anyone in a public school who might be low income and getting some government assistance on their food. They use that to index the cost and how much any kind of allocations are going to be made for people who are getting public funds contributing to their diet. So that's why we think about diets as sort of our first piece, and why we'll come back to it for our theme. But this week we're just using it to learn about the difference in minimization problems relative to maximization problems. In this lab we'll get more experience with Solver, including what happens when we mess up. So what would Solver tell us if we made a mistake what would Solver tell us if we make a mistake, one that sort of crashes Solver and won't allow a solution? And then of course one of our bigger themes, and the one we'll first introduce at the end of this, is what do you do or how do you do analysis? So one reason to do analysis is to look at the solution, think about alternatives, think about consequences, and think about sort of forming recommendations and conclusions about a specific problem. Another reason to do analysis, and to do quite detailed analysis, is for debugging. Do you have the right economics? Because there are all kinds of problems that will yield a solution from a computer, but the thing you think but you made a mistake on the input side, or you didn't think something through. And so it's usually only through sort of a detailed deconstruction, decomposition, and review of each piece of the solution that we're able to uncover those kind of mistakes. For materials, in the spreadsheet there's something called BKF diets, the breakfast diet, and it's in our workbook for this module. You have the lab handout, which takes you through some different tasks, as well as sort of introducing you to the setup of this. I believe there's an optional reading that you can look at to sort of get a layout of this problem. It's in that book by Gass, so I've copied and added that reading as, I think it's reading 3, and maybe it says optional by it. And then of course you have this optional video, and again, just like on Lab 1, I will mostly be talking about things that are either in your reading already or in the lab handout through the tasks. So again, this video is considered complementary, and you might consider it redundant, and that's why I call it optional. I'm going to talk through my thoughts about why this lab is in here, the steps I would do to complete the lab, and maybe some of the things I would stop and look at. But if you are comfortable with the reading that has been assigned, the reading is required. This video is not considered a substitute for reading the second reading, where you went through all of the minimization problems and the different errors or sort of inviable solutions that can occur. If you're comfortable with that and the idea that you could synthesize all of that, that's completely the point of this class is, and this video is considered sort of a secondary information supplement that is optional to you. Our topics, we're going to talk about minimization and what those constraints look like and how we solve. We'll look at solver, what kind of error reporting it gives you, and we'll maybe even whine a little bit about how low on detail that is. And then we'll look at examining a solution for detecting errors that solver won't pick up for us. Okay, the problem in this lab is really simple. Take two kinds of made-up cereal. I believe it says a mother wants to feed a breakfast that has a better nutrition profile than what is listed on the box of either cereal. And so she decides she's going to mix the two cereals in some kind of combination. And rather than just pouring those out, she's actually going to do some analysis and think about what the cost per unit is and mix these cereals together, pour them in the bowl in a way that makes it as cheap as possible, so that every bowl that gets poured out is the lowest cost way of getting some nutrition. And the nutrition requirements, I have no idea what thiamine or niacin are. We're in a situation where those of you with good science degrees and nutrition and or even just experience may have a much better handle on why these could have minimum requirements. But the story is you need 1, I think it was milligram, but I'm not gonna, we just know it's 1. Whatever units this constraint is, thiamine needs to be at a level of 1 or larger, and then niacin needs to be at a level of 5 or larger, and then the calories has a target of 400 or more. So we want to get 400 calories into this breakfast. 5 milligrams, we'll say, of niacin and 1 milligram of thiamine. And just like before, these coefficients in Lab 1 or in your reading, these coefficients in the constraints tell us the translation, right? So every time you eat an ounce of X1, I should point out, I think X1 and X2 here, if you follow along and look at the boundaries here, you can see X1 is really K, or crunchies, and X2 is crispies. So every time you eat an ounce of crunchies, you get 0.10 milligrams of thiamine. So that's the content of an ounce of crunchies is this, and that's the contribution to this target, right? So if you wanted to think about it another way, you would have to eat 10 units of crunchies to meet the thiamine constraint. You'd only have to eat 4 units of crispies, or X2, to meet the thiamine constraint. And so if we moved over here to the graph, we should find a line that goes between 4 and 10, and we do, and it is the thiamine constraint. I don't believe this graph is in the optional reading I handed you, because that book is set up in a kind of an odd way, and so there's over in a problem discussion set, there's like a 2-page thing on this, and I just grabbed it so we could look at it, but don't worry about not being able to find it if you start looking through that handout. But anyway, let's look at our constraint here, since you have it in these notes. This is the constraint, and this type of constraint is you have to meet this target or be above it. And so this line tells us all the combinations of X2 and X1 or Crispies and Crunchies that will meet that target of exactly 1 milligram of thiamine. You could choose to consume on this line, or you can consume something greater, right? So you can consume up in here, and that's okay because this is a weak inequality. It says greater than or equal to, and so this really gives us the lower boundary based on how much thiamine we told we're required to have. Okay, so this gray or shaded area up in here is the feasible space. If we keep moving on through here, again, the translation part, X1, this is the cost per unit. So the objective variable here, he did not write it out. I could have added it. I didn't. Sorry about that. But the objective is total cost of the diet, or total cost of this breakfast, or total cost of the meal. And so every time we choose to consume an ounce of the X1 or the K or the crunchy cereal, we are adding 3.8 cents to our cost. And that's the translation here. The translation here we've already talked about, and here or here is the same. An ounce of crunchy cereal contains 110 calories. Those 110 calories every ounce of crunchies we consume contributes 110 to this total requirement of 400 calories. Again, following over here, you can find the calories constraint down here, and it's kind of interesting because we've already we already looked at the thiamine constraint, and this one here is the niacin constraint. And so you have to be simultaneously above the thiamine constraint and above the niacin constraint, and so that's why the shaded area, this is the non-negativity constraint kicking on right here. You have to be above this, above this, above this, and above this all at the same time. And if you move on down and get to the calories constraint, you have to be above this line. This is the calories constraint drawn right here. Well, the other four constraints, the two thiamine and niacin constraints and the non-negativity constraints, have already taken care of that part for us. The feasible space is defined up in this shaded area. The constraint for calories doesn't add anything, and so we might say it's redundant. We wouldn't know that until we actually plot it and solve, and start examining the problem, right? So it's certainly a valid sort of thing to write down and say, this is part of my problem information, but mathematically it's going to have no impact, right? As long as these are the only two foods that we're allowed to choose from, and we have this level of requirement for thiamine and this level of requirement for niacin, calories is always going to be an afterthought to us. It's always going to be the case that we consume excess calories. Okay, and so this kind of analysis of my constraints, and if the ability to maybe identify something as sort of a redundant or not contributing to the boundary, right? So the boundary pieces are non-negativity, niacin, thiamine, non-negativity. Calories constraint isn't included when I go around describing the boundary. That might help us identify a problem with our solution, and we'll talk about that a little later if we've already been able to do some analysis here to think about which ones are sort of candidates to be on the boundary. So Gass, or the author is Gass, I think it's Saul or Solomon, plots two versions of the cost constraint, or the cost objective. The first one is way up here, and you can see there's lots of ways of getting a cost of 84 up here in this choice. And so just like before, when we said we can move around the objective line, or when you look at your reading from this week in the Anderson chapter, talks about graphical solutions. You can move this thing up and down to try to find the best choice. Well, cost, if profits were increasing when we moved our objective lines in this direction, then cost must be improving when we go in this direction. So going this way makes costs shrink, and our objective is to make costs as small as possible. And so if you drag this in, you would eventually find that this line has a total cost of 26.222222 2 over 9. And it is the lowest cost way of meeting all the constraints at the same time. We're getting too many calories, we're getting exact amount of thiamine and niacin that we want, and these are the quantities to be consumed. Right, so they're drawn on here. Something else we should point out, this also happens at a corner. Right, so these, let's look at this. So the feasible space here is different because it's open-ended, right? It doesn't just stop at the end of this block, it actually keeps going. And so for some reason we thought, it doesn't matter, but our maximization problems, because of the non-negativity constraints, these axes formed tended to make like little polygons that were the feasible space, so we could look at every bit of it. Well, here you can never see all the feasible space because it keeps going, and that's a good signal that the relevant part of the feasible space is going to be down here, looking at this side that looks like one of our polygons. And then of course this direction of optimization, pushing it down here, takes us to this corner, and we should note again that the corner point sort of theory or theorem is in full effect. It doesn't just work for maximization problems, it works for minimizations. Our lowest cost solution has to be either this corner, or this corner, or this corner, or that corner right there. And there is not a corner that involves the calories constraint. So another thing we might be able to do is do a little bit of algebra, check in and see what the corner points are going to be. And what you would find is the corner points that are formed by the intersection of constraints with the calories constraint get you ruled out, right? Because they intersect over here in the negative quadrant. That means it can't be relevant. Okay, not in this setup. Okay, so we are going to use this model and this setup to examine some different errors that could occur in model implementation. So I have a few of these that we should talk about, and they are covered again in Anderson. I think it's in section 6 of that chapter, but it's what I called reading 2, right? So the second half of that Anderson chapter. We're going to use this lab, and we're going to look at 2 classic issues. One is infeasibility. So you create a feasible space that is has a null population, right? So there are 0 points, 0 options that are left after you wrote down all of your constraints, or it's a set of constraints that just has an empty choice set. The simplest example you could think of is I'm going to require x to be less than 4 and at the same time larger than 5. Well, that is impossible, right? A number can't, there's no option, no value that meets both of those requirements, and so that's a null. That's a choice that it will never be found, and so that's an infeasible issue or infeasible choice. They're never that simple to find, and in fact when you write some detailed problems, it's quite possible that you put in so many constraints you don't realize it, but you've not only backed yourself into a corner, you've eliminated all corners, you've crossed everything off. The other thing we can do is end up setting up a problem that doesn't have enough constraints or doesn't have enough restrictions in all the areas that it should. You end up with an unbounded solution. Create a feasible space that doesn't check or limit the objective in some direction that it wants to keep going, and what you'll see there is solver, or any math that you might try to do to that problem, can't find a point to stop. It can't find that break to compare it to, because every time it calculates a potential solution and then considers some alternative that is a potential improvement, the potential improvement is also feasible, and it has to enter into another check. And so what happens is solver has a limit on the number of times it'll keep checking in some direction, and then it runs a test to see if something meets the unbounded condition mathematically, and if it does, it gives you that report. And then third, we have something I call the thorny problem, mostly because that's how it was taught to me. And that is the sort of, I think the picture I was described with was like a rose bush or like a pretty sort of flower thing that seems fine. In other words, a solution comes from the computer and no errors reported to you, and so you reach in, and that reaching in is like, I'm ready to do my recommendation or my analysis, and you're going to get, even though it didn't present itself in an obvious way, you get bit or you get stabbed with this thorn because the solution didn't fail. It said everything is fine, I met all the constraints, but you end up with this result that isn't right because the implementation was wrong. Something happened. Either you put a sign in wrong or the direction on a constraint wrong, and so something is wrong, and it may not, the computer is not going to be able to detect it. Now there are two possibilities here. One, it has no impact, right? So you get this solution. It turns out the error wasn't in a location that mattered given the initial conditions of the problem, and you get the true solution. The second one, the really thorny one, the one where you can get bit, is it does have an impact. It gives you the wrong optimal solution, and you start doing analysis and thinking about recommendations on a problem that is false. It is not the one you intended to solve. Okay, before we jump into that, I want to look at my spreadsheet and take you through the steps. Okay, this is the BKF diet problem, or diet sheet in our workbook. We have essentially the same formula set up. I mean, this is why these are taught together in this week. This model looks just like Lab 1. Whoops, you can see where I changed at the end of Lab 1. This looks the same as this. We've just changed our labels, and we're going to change some of the problem information, but the formulas are the same, right? Remember, these coefficients are translators. They're converters. They take an activity unit and move it and get it in the same units as the right-hand side. So an activity of crunchies, 1 ounce, contributes 0.10 of thiamine towards the 1 total of thiamine. Contributes 110 calories towards the 400 calories. Contributes 3.8 cents to the total cost. Okay, so none of the math changed except for these pieces right here, the sign, the greater than or equal to constraint in between all of these. Okay, so we have those, and then of course when we implement in Solver, we have to take care to get these signs correct and to correct to implement the fact that instead of making the objective cell here, which has the same formula, as large as possible, we need to make it as small as possible. So if I go to Solver, I can put in all the choices here. So let's go and do that now. So I've got set objective. It's going to be D4. By changing variable cells. This is where I declare my variables, and they are right here in B3 and C3. Those are right. And now I'm going to add my constraints. And all of my constraints are between here and here. And so I'm going to do a shortcut method on this one. Since in the first lab we did it line by line, as long as all of these constraints have the same sign, then it turns out you can not only use a single cell reference, but you can use an array. And so basically, as long as the sign is the same in between all of these, I can go through and say, I want all of these left-hand sides to be greater than or equal to, in a pairwise way, all of these right-hand sides. Okay? So, you'll see what that looks like when I say OK. So we end up with one line. It says, okay, compare D7 to F7, D8 to D8 to F8, and then D9 to F9. So it's doing it line by line. We chose minimization, we set the objective, we declared the variables, declared the constraints. This says make things non-negative, that's fine, and choose simplex LP, that's fine. Click on solve. Solver found a solution. Constraints and optimality conditions satisfied, and here we have those reports. I'm just going to click on OK, and you see all of our results. So just like we saw from the graphing, 26 and 2/9, right? That was 26 with 2's repeating. I believe these are the exact activity levels we saw. And then, as we noted, the calories constraint can't bind. It ends up being redundant. So that leaves only 2 constraints that could bind, and they both do. So this diet gives us the minimum amount of thiamine and niacin and some extra calories. And that's how we would sort of start our way of thinking about this. The objective, this is the lowest cost. This is how we get to the lowest cost. And when these are the activity levels, these are the statuses of the constraints. More calories than were required and exact minimum or binding thiamine and niacin. So we said we should do analysis anytime we look at one of these solutions. So let's think about a little bit of a analysis. If we wanted to think about changes to this kind of problem, one place to think about in a minimization problem is, how could I lower the cost of getting thiamine? Well, this is the lowest way given these 2 options, but what if there was like a thiamine supplement that was very cheap? Well, you might want to think about not just using the food or the diet, the choices of food to meet something that's a thiamine requirement, but maybe there's some kind of like multivitamin that includes the daily dose of thiamine and some other things that would substitute out for the food, and then you wouldn't have to worry about it, because as we see here, we're taking on a lot of extra calories, not quite, something like something like 90% above the lower bound. And as we talk about nutrition and health, one of the issues we're always concerned with is, are calories the sort of cheap item? And because we're trying to meet some other conditions in our diet, are these cheap calories building up and contributing negative health effects? So that might be one option we consider, is how do we get these things in a better way so that we're not taking on the excess calories? And then, of course, the second option would be thinking about foods that are lower in calories, stronger in this, as additions, right? So one of the issues we're always concerned with in these lower bound problems is, how much excess are we taking on, and is there some solution or some way of doing this problem? Is there another constraint that we should be thinking about that says, not only do you need a minimum of 400 calories, is there a maximum number of calories you should be taking on, right? Should you be should you be thinking that 400 is the actual target, or is there an upper bound of 575 calories and you don't want to go above that in any particular meal, right? That's a very common thing. Okay, so let's jump back and see what else we need to talk about in this in these slides. Okay, so we said we're going to look at the classic issues of infeasibility and unbounded. If you read through that section of the Anderson chapter, they demonstrate the infeasibility problem. So it's a common occurrence in complex, detailed, real-world problems, because you are thinking about you have spreadsheets and spreadsheets of data, and you say, well, okay, I'm going to translate this into a constraint, and this into a constraint, and this one into a constraint. And because somewhere else you've simplified the problem, and here you're trying to make a very detailed picture of the problem, you can end up with this condition where you say, here, I've got to be above this line and this line, while simultaneously being below this polygon, and you end up with a solution that never crosses over, right? There's no points that satisfy this block and this block simultaneously. Okay, so Solver will tell you that, and in your lab you're required to go through and actually set up a version of our diet model that gives you an infeasibility. So one of those choices one of the tasks in your lab is actually designed to throw you an infeasibility. Okay, so what's the solution to this? Well, one of the reasons that we talk about small models, small sort of building block pieces in this class is, if you ever start building a model for your project on the diet, you'll see that we go through the steps through the semester of sort of adding on things after we know we have a valid solution that we believe in and good information in the first set. Well, we increment on that and add things so as to, but we also have checks. If we start to get a failure, then we know it's the last thing we added. And so certainly for your capstone, and whether you're doing linear programming or any other method of modeling or data analysis, start small and build it out. Right? Start from building blocks, because that's the only way to be able to detect a lot of errors, and it's certainly the only way here. Imagine you started with these constraints and building those out, and then you started adding some other one on some minimum production. Well, you would be able to detect that this started here. But if somebody handed you, 2, 3, 4 spreadsheets worth of data and said, here's all the data that we're trying to work into this problem, and you just went through and wrote all the constraints out, it could be very difficult for you to find what the culprits are. And obviously, it's not clear that increment, even if you started here and added this could still be a valid concern. And so maybe the problem is the building block that you started with, but at least you would know what changes to your implementation cause the problem if you do it incrementally. Another problem is unbounded solutions, and so that's another choice or another option that Excel can tell you about. And again, in your lab this week, your lab tasks, and in your quiz, you're asked to make a change to the breakfast cereal diet model and report on which one that is. Okay, and so the lab quiz will help you, will let you know, sorry, the lab task will drive you to build an infeasible version of our model, and you'll have to deal with that. Okay, Solver will tell you this is an issue, but it also can't identify exactly where. It's usually the case. These problems are a little easier to find, and the first place to check is, did I implement something wrong? Did I mean to set max and I set min, or did I mean to set minimization and I actually set maximization? You'll see that implementation error, hopefully, and kind of go back and proofread your modeling inside of Excel, and hopefully that helps you find it. It can also be the wrong setting on the constraint. The constraint direction was set the wrong way, ends up opening up everything into one of these. You meant to have something blocked off up here, but it ended up like this, going forever in one direction. And then finally, the thorny problem. You get the solution, and Solver in Excel is happy. It's wrong because you have an error in the implementation, and it's probably the wrong sign on some kind of inequality type in a constraint. But Solver can't tell you that because Solver solved the math problem you gave it, right? So long ago there was this thing GIGO, garbage in, garbage out. You didn't mean to. You wrote everything down and did a nice problem. But it ended up, the math you gave it when you tried to implement this, it happens a lot when we have like grad students coding up problems in linear programming or even nonlinear programming. They end up making a mistake and you end up with this math problem. It's a math problem, it's just not the economic problem we were trying to deal with. It can be frustrating. It's part of why this class exists and why we go through all these examples, is to learn how to deal with these thorny problems, these thorny errors. So how to avoid? Well, one is document. So always give notes that detail, one, the setup of the problem, that let you sort of repurpose or redesign from beginning. Why did I put this constraint in? What was it supposed to do? What am I expecting from it? And that might help you go back. Some additional calculations may be useful beyond just doing what passes for Solver, and I'll actually go through and show you a little bit on this one, even though it's part of your quiz. Additional calculations to give sort of an additional check. Second, examine the solution carefully. So one of the reasons we kind of painfully go through step by step the analysis and repeat it every time is to get used to what these look like so that we can find little problems. It's likely something won't make sense, especially as we move into, as you get more experience with these type problems. And then something that isn't going to happen until Module 3, looking at the sensitivity solution. I want to talk about that in just as much detail as we're talking about setting up and solving the initial problem. Looking through the sensitivity can also be a great way to reveal that we have some kind of problem, and I'll talk about this topic quite a bit next week, or in the next 2-week module. And also decomposing, solving sort of smaller problems that can be easily replicated might be an approach that we take. So with that, I'm going to jump back to my spreadsheet and implement one of the tasks, and we'll look at that just for a second. Okay, I've pulled up your assignment, and the one I'm going to deal with here is task 4. Change the sign on the calories constraint back to greater than or equal. So on task 3, that up here, you're asked to switch the calories constraint. Here I'm going to say put it back to where it was. When you're doing these lab tasks, you'll have already done this. But for me, this was already fixed. Now we're going to change the sign on the thiamine constraint to the wrong sign, but this is the kind of problem that can happen. And this is the one that gives us the thorny problem. It doesn't lead to the error message. And so you're asked to report on the solution. I'm going to go ahead and do this because I want to talk about it just a little bit. So if you open Solver, you'll have the correct version, right, when you do this. Well, actually, you'll be fixing it, but I went ahead and changed it. So now what I have is D8 and D9, those constraints are these two, right? And those are correct. They say greater than or equal to their comparison points in F8 and F9. But the mistake we're supposed to put in is D7 compared to F7 and make it less than or equal to and not greater than or equal to. And so I've got that constraint in now. Right, so I fixed that one. Well, I've fixed it by making it wrong. And I'm going to hit solve. Oh, sorry. Looks like I messed up. There we go. So D4, the changing variables, everything's okay now. Click on solve, and it says solver found a solution. Constraints and optimality or conditions are satisfied, and we could keep the solution. So we have it, 19 cents. It looks like we've improved things, but we know we have an error. Okay, and so one way to do this, and I talked about documentation being key. Since we put these signs in here to document what we intend to do, what has happened is Solver did not get this information, but I have it. And if I visually inspect the solution I get and compare the left-hand side values to the right-hand side values, I see that I have a problem. So I know that I implemented something wrong here because the left-hand side is not greater than or equal to the right-hand side. Okay, and so essentially what has happened here, if we look back to this picture, if you take this thiamine constraint, instead of saying make it greater than or equal to, you say make it less than or equal to, then you are changing the picture here from what we had before and saying go underneath this constraint. So now you have to be above this constraint, below this constraint, and above the calories constraint, so you end up hitting this corner right here. Right, so you've made this picture, you've changed the feasibility space and giving it something on the wrong side, but the wrong side doesn't rule out finding a solution. In fact, it finds one that's even lower cost than you found when you did the true solution. Okay, so we talked about documenting and sort of visual inspection in our solution. That would help you catch this one. Another thing that I do in sort of large problems is I put another column out here called slack, and I just subtract from the right hand side, whoops, sorry, for this kind of problem we go left hand side minus the right hand side, and so it's really kind of a surplus in this case. And if you get different signs, if these are all the same, these all say greater than or equal to, but in the slack or the surplus column out here, you get different size, then you've got a problem. Because one or the other of these, no matter whether you have less than or equal to or greater than or equal to, one or the other of these is not meeting your constraint. Zeros are fine, that means you're binding. 150, it turns out, is okay because it means you are getting excess calories into your solution, but this is not okay, right? And so this becomes sort of a quick check that I can do and put these out here, especially if I've grouped all of my constraints so that all the greater than or equal to constraints are in the same area. Then you can even put in a more complicated formula. I don't know if you like to do this stuff, but you could do something out here that said like equals if this less than equal to zero comma error and you can put yourself a little error report in, so you don't even have to look and check the numbers. As long as you know that you expect all of these slack or surplus values to be 0 or positive, you can go through here and say, I need an error report that tells me that I've got something in the solver that is, solver may not be able to detect it, but I can by writing a little detection formula out here. Okay, and so we'll build up and we'll do stuff like that later on where it's more necessary or more appropriate in larger models. But you can imagine if you were scrolling through 50 constraints or even 25 on a spreadsheet model like this, or if the constraints were spread out across 2 or 3 worksheets, these are exactly the kind of tools, these kind of extra formulas or extra calculations that you need because they help you find these thorny problems. They'll also help you do some error identification and sort of zero in on problems when solver won't solve. With that, that completes all of our optional videos for this week on the labs. So if you have chosen to go through this optional video, I think it will be helpful. But this is sort of the theme of all of these, so use it as a guide on whether you continue looking into the optional lab videos that come up. Some of them will be required because that's the only way I'm going to be able to present some material to you. But in this case, where I'm kind of overlapping with the reading and the lab handout instructions, I wanted to give you these optional sort of look at how I do these problems and talk through them. All right.